We are officially past Thanksgiving, and that means that I can play Christmas carols. I love Christmas carols. It's the one kind of music that everybody knows the words to. They're the best. But you have kind of a different take on Christmas carols, though. And this is my favorite one this year. Yes, we are doing some dubstep Christmas, because that's what I like, so that's what I have to listen to. And I went in and did the wig thing. I thought it was a good way to go for 1 week. This is my favorite wig, because it has little tassels, and everything's better with tassels, yes. Anyway, this week's video is on electric potential. I can't really call it voltage because it's not. That's what it's measured in. And about energy. So let's get started. Okay, electric potential is basically our thing that we use to figure out energy. We can also use it to find electric field. They're all kind of interrelated, but it's the thing that tells us how much electrons want to move from one place to the other. And it's kind of a hard thing to conceive of, so we gotta use some tricks, sort of. It's what we use to find the electrical energy too, and it's called V for voltage, and it's measured in volts. And we want to call it voltage, but we want to try to keep ourselves from doing that and call electric potential, because that helps us keep straight what it is, and since it's such a hard concept anyway, we want to try to do that. Feel free to correct me if I call it voltage, because it's not, it's electric potential. And the same way we used height when we were talking about gravitational force and energy, like mgh. Potential is similar to that for electricity. It's what we use to calculate the energy. And so a lot of times we even draw pictures where we use height to represent different potentials. If we go from 0 volts to 5 volts, we have to go up, and so we have to give it some energy somehow. And if we're going from 5 down to 0, we can get some energy back out, the same way we did for gravitational heights. So a lot of times we think of V as the H of electricity. Wow, I thought this didn't work there. You get it. Tricity. Closer. Ha. Anyway. Notice that when we have two lines of charge in this picture right here, we have an equation for the potential that is just the electric field times the distance between them, and that's a constant constant electric field between those, and the voltage is the difference between the two plates. But really the one we use the most often is this V equals kq over r. kq over r, and that's the potential from any given point charge. So this picture down here has a point there, and then we have different amounts of potential at different distances away from it, and we can figure out how much that potential is by putting it into this equation here. And just to remind you, the electric field and the force equations are very similar. Notice they all have K's and Q's and R's, so we have to try to remember in our head how they're different, and V as an R instead of an R squared like the electric field and the force ones do. So that helps us keep them apart. And again, the AP uses 1 over 4 pi epsilon naught, but we're probably going to use K, and K being 9 times 10 to the 9th. One nice thing about potential is that it is a scalar, so we don't have to use all those sines and cosines that we're so out of practice in using, and what causes so many problems in the test. So remember, V just adds as a scalar, so we can find the V from different charges. So if we have a plus there and a minus there, we want to find the V there. We can find the one from this one, which will be positive, one from this one, which will be negative, and we can just add them because it's a scalar instead of a vector. We don't have to worry about sines and cosines and directions. Another thing about V is that it's constant inside a conductor. We talked earlier about electric field being 0 inside of a conductor, and electric field gives us a potential, and so if there's no potential difference between things, there's no electric field there, and so that's why there's no V inside of a conductor, because their electric field, the V is a constant, because if there's different in V's, delta V would give us electric field, and there isn't one inside there. And also there are 90 degrees to electric field lines. So when we did electric field lines, remember we said that it was lines going away from plus and towards minus. And if we had to draw the V that are constant levels, we can draw them as lines going around each of these two things. And they're very similar to topographical maps, those lines are. And you could put positives and negatives on them. So if we took this and put it sideways and used our height analogy, this positive would be way up here, this negative would be way down there. If this was our 0 point, we could draw a little thing that showed what would happen to our potential. And a constant line would be just slicing into each of those as a nice little circle. I'll explain that more in class. Because we talk a lot about the inside of conductors, we end up having to do some problems. The AP likes to do problems on what's called nested spheres of charge. And so what they'll do is they'll put a circular ball here and another one inside that ball, and they ask us things about what the electric field and the voltage is at different places, like inside both of them, inside just one of them, or outside both of them. And they'll put different charges on each one over here, so we have to know what happens inside of them. And remember that basically inside both of them, the E field is 0. And so if we get on this inside area, there's no electric field. If we get outside the first one, we're in this area here, the electric field from the outside one will be 0, but the inside one is going to be the equation, kq over r squared. And so we have to figure out what it's going to be, how far away we are from this one, but not from this one in here, but not from that one out there, because that one's a 0. If we get outside both of them, electric field is going to be kq over r squared for this one and kq over r squared for this one. As it moves away, it gets smaller for both of them. And for the voltage, it's constant if you're inside of it. And so if you're inside both of them, it's constant. If we're outside of this one, it's constant from the blue one, but not from the red one. So it gets kind of complicated, so we're going to draw you a better picture the next time. So here's our better picture. These blue things here represent the two nested spheres. And so we're in both of them. I said already that my electric field was 0 for both of them. The voltage is constant for both of them. See, I have a Q1 over R1, Q1 being my charge for the first thing, Q2 being the charge for the second one. Q1 over R1 because I'm constant and I'm inside of it, and the distance that I use for the constant thing is the radius of the whole sphere. And since I'm inside of this one also, I use this constant charge and this constant radius here, so I get a constant value, all the stuff in here. Once I get outside of the first one right here, I get an electric field from the interior one, and I do kq1 over r being the radius where I'm at, so it can change as I go in between those two, but I get a 0 from the outside one. The voltage gets a little more complicated. My voltage is constant from the outside one because I'm inside of it, but in the inside one it's no longer constant. It uses the little radius where I actually am to calculate it, so that changes as I move in between the two. And when I get outside both of them, my electric field and my voltage are both changing with the radius, and I have to calculate each of them based on my position. Inside, constant voltage, no electric field. As I get outside of each one, I have to start calculating the changing electric field, and constant V inside and change as I get outside each one. So those problems can be a little confusing, but like if you look at the back of this picture and maybe look back at the one without any of my marks on it especially, and try to think through that and ask any questions you have, we'll get through it. Another way to visualize this is with a little graph, and so we did a graph of one sphere. So if we have one sphere up here that we're getting outside of, as our r gets bigger, this is our r, if we're inside of the sphere, it's a constant value based on the r that's on the outside, and it's a constant v and it's a 0e. And right as we get to the r, this one jumps up to a pretty big value, because remember our r is on the bottom, so when we're close it's a big value, and as I go away it goes off as r squared. My v up here was at a constant value, and now it starts dropping off as an r, so it's not quite as steep as the bottom one right there. Both of them fall off as r goes, but one goes as r and one goes as r squared. They're both k, q, so the top part's the same, the bottom part just makes this one steeper than that one. And the electric field is 0, and the voltage is constant inside the sphere. Phew, that was a little complicated. We need a break for after that. This right here, is the pie that I made for Thanksgiving, and I'm going to be having some leftover pie for my snack. This is a blueberry buttermilk pie on a gluten-free crust. Ooh, and it is really, really, really good. I hope you had some good pie. I don't know why, but pie to me is Thanksgiving. Maybe it's because I'm vegetarian, so it can't be turkey. Oh, mashed potatoes too. I have some good mashed potatoes. I still have some leftovers of that, maybe after the video. Alright, back to physics. So potential energy. As electric potential is just like every other kind. We can set it equal to other kinds of electric energy. Other forms of energy, so kinetic energy or other potentials. And notice that it's V that we use to find it. We take our voltage times whatever charge we're going to put there. So just like electric field was a quick way to find the force, voltage is a quick way to find the energy. And that's why it's similar to height, because height was a quick way for us to find gravitational potential. And this picture right here is one of the biggest examples that they use for this kind of energy. They'll say we have a capacitor, which is just basically two plates, one of which has negatives, one of which has positives. We put an electron right here. We know that electron's going to want to leave and go away from the other electrons. And we want to know how fast it's going to be if we put one little hole over on this side, so it's attracted by those, it's going to be going through. We want to know how fast it's going. We can set the electrical energy, QV, equal to 1/2 mv squared. We have to know the mass of an electron, and we can find the speed that it leaves the capacitor at. That's AP's favorite one with electric potential. We can set it equal to any kind of energy, really. And then we do different kinds of problems later on to do that. This right here is just telling us that this is very similar to our work formula, because if we take the force, the electrical force, K, Q1, Q2 over D squared, and multiply by the distance that is moving, which is just the D, we get our equation for electric potential energy, which is K, Q1, Q2 over R. Yeah, and these K's and Q's and R's are getting a little confusing. So we make a little chart to help us out with that. And we make a little four square thing. Notice this says scalar here. This one's vector. We have one charge and two charges, so we can keep them straight in our head. And we know that the two vectors are force and electric field. And both of those have R squareds in them. So R squareds go with vectors. Potential and energy are both scalars. And those only have an R in them instead of an R squared. Potential and electric field are the ones that we use to calculate the other one, and those only have Q in them, not Q1, Q2, because we're setting it up and we want to be able to put a charge in there and figure it out really quickly for a lot of different things. And the things that have two charges are the ones that we actually use mostly in problems where we're actually going to other types of energy other than electrical energies and forces. Notice that as we move this way on our graph, we have multiply by Q each time. So we're going potential to energy, we have multiply by Q. We're going from a field to force, we multiply by Q. Obviously, when we go backwards, we divide by Q. I want to put dots. And when we're going from scalar to vector, we divide by R. Notice it's R squared and R, so we take it and we divide by R. If we're going back the other way, we would multiply by R. But they're all really interrelated, so it's good to have this in your head to keep them straight so you don't mess up and use the wrong formula at the wrong time. We already sort of described some capacitors, so let's go ahead and do some talking and some equationing about them. Capacitance is the ability of two plates to hold charge. It's always two plates, and so you always have some kind of charge. Always one's going to be positive, one's going to be negative, and you're going to have a voltage across them. Say this is V2 and V1. And so our basic equation for capacitance is how much charge something can hold for the voltage that you put across it. So these over here are pretty big capacitors. And this is what a small capacitor looks like, mostly in computers and small circuitry. But like these two right here, those are big ones. And you gotta watch out if you ever see one of those in something, because you can really hurt yourself with that. So if we know the capacitance, we can find how much charge it will hold. But finding that capacitance is what this equation is for. And there are a lot of factors that go into that. One is a constant having to do with the substance that you're in. The second is a constant that has to do with the universe that we're in, that E sub aught one. But the main thing about it is the area that overlaps in my two capacitors. I said it was two plates, and I kind of tried to make it 3D in this picture so you can see the two different plates, and then the distance apart they are. The closer you get together, the more charge they can hold, because the more they attract each other, and the more area you have, obviously, the more charge it is. So if you have two plates, and I'm showing to you from a side view, it's only this bit area that I care about, not the other parts over there. And so that's how all the variable switches that you see are work. What you have is you have two half circles, one of which is attached to a knob, and then when you twist your knob, this one moves up there so that the area that it covers up gets bigger and bigger and bigger, and so we get a higher and higher capacitance, and that allows us to have variable switches on our lights, which is very convenient. We have 3 energy equations for capacitors, because really that's what capacitors are for, is to store charge. And so we want to be able to put charge in them and then use them to do other things. And we take the first one, the U equals 1/2 QV, and we put the definition of a capacitor into one or the other of those two things to get the other two equations. But because we're doing energy so much with the capacitors, we want to be able to use whichever formula works for whichever situation we're in. And we can set these energies equal to any of the other ones. So we could say we have a capacitor that's fully charged with so much voltage and so much charge. 70% of that goes into making a motor run, because that's what electric cars are, is a big capacitor and make it go. How fast is the car going to be going? So we can set the energies equal, just like any other energy we have. As we get close to the end of each chapter, there's always requests for a listing of all the formulas. You have that one that has these things on there, but a lot of people like it in what we use in class as opposed to what AP does. And so all these red ones over here are what we actually use. And you're free to do either one of them. Notice that these two have 2 different formulas. You need to know both of them. This one has 3. I don't know why I didn't put 3 there, but it has 3. Make sure you know that. And again, anything for past quizzes, the emphasis on that, again, will be on things that we're using for this chapter as well as for having used them for past ones. Snowflakes, some of my favorite things in the world. And when I moved down to Texas from Chicago area, I miss snowflakes. And so we're going to have to do something about that probably next time I see you.